Alright everybody, so today I wanted to talk to you about common ions and their effect on solubility. So far we've done KSP, finding both the molar solubility or given molar solubility finding KSP. Those were in the previous video. And so now we're going to have a situation where we have a common ion. So let's take, for example, if we were to have AgF and we were to dissolve this in water and have Ag plus and F minus. And let's say that I gave you, a KSP for this, and my KSP for this would be maybe just an easy number, 1 times 10 to the negative 10th. So now we have a KSP for this. If we were to find the molar solubility, we would have 0 and 0, plus x, x and x. So we would have x squared equals 10 to the negative 10th. And so x, the molar solubility, would be 1 times 10 to the negative 5 molar. So keep this number in mind here, because this is our solubility if we were to have just pure water. Now, what if we have a common ion? So with a common ion, what ends up happening is we have some sort of other salt that's very soluble. Maybe, for example, like NaF. NaF is a soluble salt that has a group 1 metal. And so let's say that we decide that we're going to add 0.1 molar of NaF to a solution that contains saturated AgF. And so now with this one here, what ends up happening is if we rewrote our equation out and we did that, we would have AgF yields Ag plus F minus. But now instead of 0 and 0, we would have 0.1 molar for F and 0 for Ag. Now we'd still get our plus x and our plus x, but we'd have 0.1 plus x and x. When we went to go plug that into our KSP, we'd have KSP equals x times 0.1 plus x. Now because the x is going to be a really small number, we can go ahead and neglect that. And we would have our KSP, which is the same, 1 times 10 to the negative 10th, equals 0.1x. When we solve for x, we get 1 times 10 to the negative 9th. And so my point is this: when we have a common ion, the solubility goes down. It's going to cause there to be a decrease in solubility. And this is sort of like an application of Le Chatelier's principle. If you increase one of the concentrations of the product, it causes the reaction to shift to the left, away from the soluble ions towards the solid. And so now we have this situation where x has dropped from 10 to the negative 5 molar, wasn't very soluble to begin with, but all the way down to 10 to the negative 9 molar, so pretty insoluble. So the idea here is that when you have a common ion, it's going to decrease the solubility of this compound. And here I give you another example where we have sodium chromate added to lead 2 chromate. And so you could try this one on your own. I can give you some numbers. Let's say that you have your lead 2 chromate. And let's say I give you a KSP equal to 1 times 10 to the negative 12. And so then I'll ask you, what's the molar solubility? And then let's compare that to what if we add 0.5 molar sodium chromate? And then what's the new molar solubility? So this will give you an idea of, of how this works. Let's see what you come up with that. Should look really similar to the previous question that I just did for you. So try that one out for me. Here's some more practice for you, and you can try this now with some zinc hydroxide. This one has a really low solubility. So they want you to calculate the zinc hydroxide molar solubility when the pH is 9.35. So that one's kind of cool because it's incorporating pH into this type of problem. And so with the pH, you could find the pOH, and the pOH for this would be 14 minus 9.35, so that would be 4.65. So our OH minus that exists already is equal to 10 to the negative 4.65. So now we have some OH minus there instead of having basically 0 OH there when we talk about a neutral pure water solution. So again, find the molar solubility. And then also try something like part 2 down here, where I go ahead and I mix some zinc nitrate with NaOH. And they ask us what the concentration of zinc is in the existing. And this one's really challenging. This one's from an old AP exam. You're not going to really see anything like this on the test that I give you, but give it a try, and then we can go over it in class and kind of talk about, what it is that we actually saw. Okay, here's another example that I wanted to talk to you about, which was how pH affects the solubility. And so this sort of relates to what we saw with the zinc hydroxide, except in this case here, we actually have another chemical reaction that's occurring. And so in this case, I have this pretty insoluble salt here, calcium carbonate. And if I start adding HCO3 to this, the HCO3 will actually react with the ion here. So when I lower the pH, it will react with this carbonate ion. And so the H3O plus that I add will react with the CO3 2-. As a result of that, you'll form H2CO3 and HCO3-, and both of these are more soluble, and because of that you actually can increase the solubility. And this is sort of exactly what's occurring when you have something that's made out of limestone and you subject it to acidic conditions like acid rain. So if you were to have acidic water and it were to react with this calcium carbonate, it would start dissolving away these limestone, statues and sculptures. And that's what we see happening with the effect of acid rain from the environment on these types of insoluble compounds. The last thing that I want to talk to you about in this particular video, and the last thing for this whole chapter, is predicting if a precipitate will form. And so let's take something like if I were to add some sodium fluoride and I were to add that to some lead nitrate. And if you were to do a double replacement reaction for this, we would have PbF2 forming plus NaNO3. And if we were to balance this, we would need 2 NaFs for every 1 PbNO3 too. And our reaction for this, if we were to write the net ionic, would be 2F- plus Pb plus 2 yields Pb plus PbF2. The thing is that this starts an equilibrium, and so we form an equilibrium and we go back the other way, and so now we have this solubility. And they'll give you a KSP for this. They'll say the KSP for this is equal to, I don't know, 1 times 10 to the -8th or something like that. Trying to use easy numbers here just to get the concept across. Now, the question is will the precipitate form? So, let's say, for example, that I decide that I'm going to mix, 10 milliliters of 0.001 molar NaF to 10 milliliters of 0.0001 molar PbNO3 So now we're going to mix those two together and see if a precipitate forms. I'm going to move into the other room before the next class starts, and we'll continue. All right, everybody. So to continue where we were before, so I gave you the concentrations of each of the reactants in this case. And so now what we're going to try and do is we're going to see if a precipitate forms. And this is a little different from what we've done in the past because in the sense we want to see if there's enough ions to saturate the solution when they react. So let's go through this. Let's say that I have my 10 milliliters of 0.001 molar NaF. And all that I'm really interested in are the ions that are reacting. And the ions that are reacting in this case are my F minus and my Pb plus 2. So let's find the moles of the F minus. And we could do this in millimoles too, just to keep things a little bit easier and simple, straightforward. So we have 10 milliliters and we have 0.001 molar. So now when I go ahead and I look at that, I times them together, and so I would have 0.01 moles of F minus, and for my Pb I would have 0.001 moles of Pb plus 2. So now I have these two that are my moles of each one. So now I'm going to take these moles of each of these ions and I am going to change them back to molarity. And why am I going to do that? Well, I've added two solutions together. And so now the two solutions, their volumes are additive. So instead of having 10 milliliters of each, I have 20 milliliters of each. That means that my volume is doubled, my molarity has gotten cut in half. So my F minus really becomes 0.005 moles, and my PB becomes 0.0005 moles per liter. So now I can take this and I can plug it into my KSP. Now I'm not sure if a precipitate is going to form, and if I'm not sure that a solution is at equilibrium, well, in that case I would use a QSP. It looks the same as KSP, just like Q looks the same as K. So we have our PB plus 2 and our F minus squared. So now I go ahead and I plug in my values. For PB, it is going to be 0.0005. For my F minus, it is 0.005 squared. So now let's go ahead and calculate this. Let's see what we get when we do this. So going ahead and doing our 0.0005 times 0.005 squared, we are going to get 1 times 10 to the negative 2468. Wow, who would have thought that I would have worked with that? Is that what they get? Oh, let's actually make the exact number so that it works. So we're going to get 1.25 times 10 to the negative 8. Now, this Q value here, it's greater than my K value. Since I have more ions than I am supposed to have in solution, my Q is greater than my K, I would be saturated. And yes, when I'm saturated, a precipitate will form. Now, if you want the rules for Q versus K, I listed them up here. So when Q is equal to K, you're saturated, a precipitate will form. If the Q is greater than K, then a precipitate will form. If Q is less than K, a precipitate will not form. So let's try one more problem that you can do on your own, and we can practice it in class together. Let's say, for example, that I was going to add sodium chromate to silver nitrate. And let's say that I had 50 milliliters of a 1 times 10 to the negative 4 molar solution of sodium chromate, and I had 50 milliliters of 0.0025 molar AgNO3. And let's say that I give you the KSP for Ag2CrO4 is 3.5 times 10 to the negative 12. So will a precipitate form? Try the problem, let's see what you come up with, and we'll talk about it in class. All right, that's it for KSP. Thanks so much for watching.